Hello everyone, in this video we're going to be looking at calculating equilibrium concentrations from initial conditions. I have a sample question here, but before we go into the sample question, I want to refer to these general steps that will help you solve each of these questions in this type of material. The general steps we need to follow are write a balanced equation, just like everything in chemistry. Make sure we start with a balanced equation, followed by calculating any concentrations. Reminder, concentration is equal to moles over volume. And in our case, we're going to be dealing with the units of moles per liter. We then need to write an equilibrium expression. We referred to these as KEQ or KC expressions in previous videos. We then want to fill out this thing called a rice table, which is going to be my focus for the next few minutes, with both the knowns and unknowns from the question. And then finally, we want to solve for an unknown value. We want to actually answer the question that's being asked of us. So moving over to this thing called the rice table, you can see it's just a fancy table with 4 rows, and each column is broken down to represent a component or species of our reaction. Reaction R just is physically taking each component into a column title. This helps us stay organized. I stands for initial concentrations, which we're going to solve in a minute. C stands for our change. Are we increasing or decreasing as we go from initial towards equilibrium in regards to our concentrations? And then E stands for the concentrations at equilibrium. This is important because this is where we can solve for Kc. We need those values. So first things first, let's write a balanced equation. Well, this equation is balanced. It's an abstract equation, so we're good. 1 mole of A, 1 mole of B reacts reversibly with 1 mole of C and 1 mole of D. Next, we need to calculate concentration. We can see that our units up here are in moles. So we need to take our moles and divide by our volume. Luckily, our volume is 1 liter, so it's not going to be too stressful on our heads. So it says if 0.65 moles of each reactant is placed in a 1 liter container, calculate the Kc if 0.43 moles of each product is present at equilibrium. So we go through and we have calculated our concentration. Okay, I'll fill it in the table in a second. It's not a hard one for this one. We're going to write our equilibrium expression. So our Kc is going to equal to C and D. Remember, square brackets represent concentration, and that's going to be over A and B, our 2 reactants. So we'll multiply those. Okay, so we're checking off these as we go. Now we're going to fill out the rice table with knowns and unknowns. Well, we know at the start, each reactant is placed into a 1 liter container, and it's 0.65 moles. So 0.65 moles divided by 1, that is going to equal 0.65 molar A and 0.65 molar B. They're placed into a container. So that tells us that there is no C and no D. So those values are 0. Those are my initial concentrations for the system. That's great. Now I want to figure out what else is in the question. It says that we have 0.43 moles of each product present at equilibrium. Well, 0.43 divided by 1 is 0.43 molar and 0.43 molar. We now have our knowns and our unknowns in the rice table. Next thing to do is figure out how are things changing. Well, I'm going from 0 to 0.43 moles. So I've increased by a variable of x. Okay. I'm just using x. You can use any letter you want, but I'm increasing by an unknown amount. And we actually know this amount in this case, but we're going to leave it as an unknown for the purpose of this question. When I look back up here at my ratio, I can see that the stoichiometric coefficient of C is 1, and the stoichiometric coefficient of D is 1. So we have a 1-to-1 ratio of each product. So if C goes up by a value of 1x, that means D is also going to go up by a value of 1x. They're on the same side, they're both products, and it's a 1-to-1 ratio. So they're going to go up by the same amounts. If my products are increasing, that means my reactants must be decreasing. I have to get the mass and matter from somewhere. So we're going to be really focusing on that forward reaction in this case as we strive to reach equilibrium. What this means is that I solve for x, my change, and I can take that change and subtract it from my initial conditions to figure out what are A and B at equilibrium. So let's do that really quickly. You can sometimes do this right in the equation. Sometimes I like to do this, right in the table, 0.65 minus x, and this one is going to be 0.65 minus x, just as a reminder to myself of where I'm getting these numbers. And then I can come over here and say, oh, you know, x is 0.43. So X is equal to 0.43 molars, or molar, that's the change. So if I go 0.65, subtract 0.43, I get 0.22 and 0.22. So those are my concentrations at equilibrium, all based on this idea of change. So if I go through and fill these into my equation, I would get 0.43 multiplied by 0.43. I'm realizing that looks like a 9. I don't know what happened there with my pen. And that's going to be divided by 0.22 and 0.22. We're going to get a final answer here once we do the math of 0.244. Nope, sorry, I looked at the wrong page there, 3.82. Okay, so there's our Kc expression, or a Kc value for this expression. Remember, if it's over 1, it's going to favor the products. If it's under 1, it's going to favor the reactants. And we're just a little bit above 1 when we think about the grand scheme of things. 3 is not that much bigger than 1. So we're going to slightly favor the products in this equation. And we can see that here in our equilibrium concentrations. We can see that C and D are slightly higher than A and B. Okay, so we're favoring the products slightly. So if that is starting to make sense for you, great. I'm going to move on to question number 2, and I would ask that you pause the question or the video at this point in the time and actually try to solve it. Okay, if you're still not comfortable, just keep on going and follow along with me. All right, hopefully you actually took that chance to pause the video and attempt this question yourself, and we will get started now by answering it. So at a certain temperature, the equilibrium constant for the following equilibrium is 82. If 0.83 moles of I2 and 0.83 moles of Cl2 were placed in a 10-liter flask, that's a good thing to note. Our concentration is going to be a little different this time. What would the equilibrium concentration for Cl2 be if the final equilibrium concentration of ICl is 1.0 moles per liter? All right, it's a pretty big question. A lot of information in there. Let's break it down piece by piece, and that is the purpose of using the Rice table. So remember, start by balancing the equation. 2 moles of iodine reacting with 2 moles of chlorine to give a single mole of iodine monochloride. Well, we just got to put 2 there. Now we're balanced. Second thing we want to do is start filling out the reaction table. So let's put I2 here. Okay, remember our reaction, we're just doing this to organize our information. And ICl. You'll notice I didn't put the coefficients into this line, this row, because we're just using this as a note to keep track of what we're doing. Next, we have to do or solve for the initial concentration of each of these species. Well, concentration is moles over volume. We know this from previous lessons. And for an example here, if I was to take 0.83 moles of I2, okay, so I'm taking that right there, and divide it by that 10 liters. Okay, so 0.83 moles by 10 liters, that's going to give us 0.083 molar solution. And that's the case for both I2 and Cl2. So we can write that in. 0.083 molar, 0.083 molar, and ICl at the start is 0. It's asking us what is the final concentration of Cl2, so this is where we're aiming for. I'll put a little question mark there. And it says that ICl at equilibrium is 0.10 molar. So we have to increase by a value of 2x. Remember, the 2 is going to be in relation to the stoichiometric coefficient. And if this goes up by 2, these go down by 1 each. Okay, it's a 1-to-2 ratio. If my products are going up, my reactants have to go down. Again, conservation of mass. Matter has to come from something. And when I look at it, it's a 2-to-1 ratio. A 2-to-1 ratio. That's why it's 2x and 1x over here. Okay, so that's not bad. Next thing we have to do is figure out what is x. Well, let's look at that from the perspective of ICl. So we know that we start off with 0, we add a value of 2x, and we magically get to 0.10 molar solution of ICl. So the 0 is insignificant, so I'm just going to drop that and go 2x equals 0.10, and that's going to be molar. And then we just divide by 2, both sides of the equation. Our 2's will cancel, and we're left with x equals 0.05 molar. Okay, so that's our change value. So now that I know what x is, I can easily go back and fill in my equation. Over here, I have 0.083 molar solution of Cl2, and I'm going to lose 0.05 as we go towards equilibrium. Well, that's just going to equal 0.033, and it'll be the same thing for I2, 0.033. So that is the answer to the question right there. My concentration of Cl2, okay, so my concentration of Cl2 is going to equal 0.033 molar. In this question, the equilibrium value, Kc of 82, we didn't need it. Okay, we had a starting point right here and a final point at equilibrium, so we're able to algebraically determine what is x and then just use that to fill out the rest of the table. That's not going to be the case in the next question. So please take a moment, pause the video, try this question out yourself, okay, test yourself, and then unpause the video and we'll go over the answer together. All right, welcome back. This question is going to be a little bit longer. We have some math to deal with, but at the end it's not going to be that much more difficult. So the question states the equilibrium constant for the following equilibrium is 4. If at equilibrium the concentration of H2 was 0.54 molar and F2 was 0.54 molar, what was the starting concentration of HF if no products were initially present? Okay, so let's start by checking, is our equation balanced? It is not. We'll put a 2 in front here. Like it was 2 moles of hydrogen, 2 moles of hydrogen, 2 moles of fluorine, 2 moles of fluorine. Okay, so we're good there. Next thing we want to do is figure out, do we need to calculate concentrations? Luckily, this question gave our values in molarity, so we're good. We don't have to calculate concentrations in this question. Next, we want to move in to filling in the rice table. So let's put our hydrogen monofluoride, our hydrogen gas, and our fluorine gas in as column headers, just to keep our data nice and clean. And then we're going to put in our initial concentrations. Okay, it says we are looking for the starting concentration of HF. That's what we're looking for. If no products were initially present. So that's 0 and 0. Okay, so those were initial concentrations. I got that from that line right there. And then we want to figure out what else do we have in this question. Well, we know the concentration of H2 and F2 at equilibrium to be 0.45 and 0.45. Okay, so that means we're going from 0 to 0.45, so that has to be a positive increase. And if these are going up by x, well, it's a 1 to 2 ratio, so HF must be going down by 2x. Okay, and then we need to figure out what is this value here as well. Okay, luckily we know that if we have the Kc value, okay, of 4, we could solve for this value here at equilibrium. And if we know this value at equilibrium, we can work backwards to find what is the initial concentration of HF. So that might be a good thing to do, is maybe write down your goal of what you're trying to solve as an equation. So the concentration of HF initial is going to be subtracted by a value of 2x, and that's going to give us the concentration of HF at equilibrium. So I'll put that as E, subscript E. So there's our ultimate goal. So we got to solve this. We know what x is. X is just going to simply be 0.45. So if we solve for HF at equilibrium, we can work this out algebraically and work backwards to get the initial concentration. So let's go ahead and write our Kc expression. Kc is going to equal H2 and F2 divided by HF raised to the power of 2. Remember that 2 is coming from our coefficient in the equation. We can go ahead and fill in our values. Well, Kc equals 4. We know that the numerator is going to be 4.5 and 0.45. And the denominator is what we don't know. And I'm just going to put that in as a variable of E to represent the unknown equilibrium right now. And maybe I should also give that a subscript of HF, just so we remind ourselves. I probably should have done that the other way, HF at equilibrium, but I won't correct it at this point. Okay, so that's going to be squared. We can see that 4, that's something that's a perfect square. We can take the square root and get 2. And these things as well, if I was to work it out mathematically, it'd be the same value squared. So maybe let's just do that for clarity. We'd have 4 equals 0.45 squared, because it's just the same number multiplied by itself, divided by EHF squared. We can then introduce a square root on both sides of the equation to simplify the process. And in doing so, we're going to get rid of these squares. Okay, so what I'm going to do is just jump over here to the right. Okay, so just come on up. And we're going to get 2 equal to 0.45 divided by EHF. Okay, we're going to multiply both sides by E, then we're going to divide by 2, and we're going to figure out algebraically that E is equal to 0.225. That's great, because now we can come up here and fill in this original equation that we wrote to keep things in order, and HFI is going to equal minus 2, 0.45. Remember, the 4,5 is coming from this part here in the equation, and that's going to equal a final concentration value of 0.225. We got that from our Kc expression. We then just solve this algebraically. We do some math, move things around, and we get HFI, so the initial concentration of hydrogen fluoride, and I should go back and put these in square brackets too, sorry, is going to equal 1.125 molar. So there's quite a bit of information you can get from these questions, and there's quite a variety of ways these questions can be answered. What's important here is just to think logically, use the rice table as a tool to organize your information, and to just step through those basic steps. Start by balancing the equation, convert anything to the concentrations that you need, making sure that it is in moles per liter or molar, then filling out what you know and don't know in the rice table, and then just thinking about it mathematically. How can I work out the unknowns? Whether that's just solving for Kc simply, if you're given all the equilibrium expressions, or working your way backwards to solve for an unknown initial concentration by first solving for Kc and an unknown, and then using that to work up the table back to initial concentration. I know this is a lot of information. This video is quite long, and if there are more questions, I will try to post a second video with a few more example questions. Thanks for watching.